Welcome to today's problem walkthrough. We'll be tackling LeetCode problem number 1733, titled Minimum Number of People to Teach. This problem is a fascinating blend of graph theory and optimization, challenging us to think critically about communication and language learning within a network. Let's dive in and explore how to solve it step by step. In this problem, you are tasked with managing a social network of n people, where each person is labeled from 1 to n. Every individual in this network speaks one or more languages, and the challenge lies in ensuring that friends in this network can communicate with each other. Communication between two friends is only possible if they share at least one common language. The goal is to determine the minimum number of people who must learn a new language so that every pair of friends in the network can communicate effectively. The input includes three main components: an integer n, representing the total number of people in the network; a 2D list called languages, where each sublist specifies the languages spoken by a particular person; and a list of friendships, where each pair indicates a friendship between two individuals. The output is a single integer, representing the minimum number of people who need to learn a new language to resolve all communication gaps in the network. Let's look at an example to better understand the problem. Suppose there are three people, and the languages they speak are given as follows. Person 1 speaks language 1, person 2 speaks language 2, and person 3 speaks both languages 1 and 2. Their friendships are represented as pairs. Person 1 is friends with person 2 is friends with person 3, and person 3 is friends with person 1. The output for this example is 2, meaning that two people need to learn a new language for everyone to communicate. We will explore the reasoning behind this in the next part of the explanation. Breaking this example down further, we examine the friendships one by one. For the pair 1, 2, person 1 and person 2 do not share a common language, so they cannot communicate directly. For the pair 2, 3, both individuals share language 2, so no additional learning is needed. Similarly, for the pair 3, 1, both share language 1, so they can communicate. To resolve the communication gap between person 1 and person 2, we have two options: either person 1 learns language 2, or person 2 learns language 1. Either way, two people need to learn a new language in total to ensure all friendships have a common language. This is why the output is 2. Now consider a second example. Here, there are two people, and their languages are as follows. Person 1 speaks only language 1, while person 2 speaks languages 1, 2, and 3. They have one friendship, represented as the pair 1, 2. In this case, person 1 and person 2 already share a common language, which is language 1. Since they can already communicate, no one needs to learn a new language. Therefore, the output is 0. Let's go over the problem's constraints next to ensure we understand the boundaries of the input and output. This problem comes with several constraints and edge cases worth noting. For instance, if all friends already share at least one common language, the output will be 0, since no one needs to learn anything new. Similarly, if there are no friendships in the network, no one needs to learn a new language, and the output will also be 0. On the other hand, if each person speaks a unique language and there are many friendships, a significant number of people may need to learn a new language for everyone to communicate. Lastly, if there is only one language spoken across all individuals in the network, the output will always be 0, as everyone can already communicate using that single language. These edge cases help clarify how the problem behaves in various scenarios. To tackle the problem of determining the minimum number of people who need to learn a new language, we begin by considering two main approaches. The first is a brute force method, which is conceptually straightforward. For each language, we simulate teaching it to all individuals who currently cannot communicate with their friends. By iterating through all the friendships and languages, we can calculate how many people need to learn each language to bridge communication gaps. The result is the minimum number of people across all languages. However, this approach has a significant drawback. Its time complexity is m*k, where m is the number of languages and k is the number of friendships. This makes it inefficient for large inputs with numerous languages or friendships. Alternatively, we can use an optimized approach based on set operations. This method focuses on pre-computing the set of people who cannot communicate with their friends. For each language, we then calculate how many of these people would need to learn it to resolve communication issues. By narrowing the scope to only problematic friendships, this approach avoids redundant checks and improves efficiency. To implement this optimized approach, we start by identifying problematic friendships, which are those where the two friends involved do not share a common language. Next, we determine the set of people involved in these problematic friendships, since they are the only ones who may need to learn a new language. For each language, we count how many of these individuals do not already speak the language and would need to learn it. The total time complexity of this method involves pre-computing the problematic friendships in O, K, and iterating through all languages and the relevant people in O, M**n, where n is the number of people. This results in an overall complexity of O, K plus M**n, which is far more efficient than the brute force approach for larger inputs. Additionally, alternative heuristic methods, such as greedy approaches, can be considered. These methods prioritize teaching the language that reaches the largest number of people involved in problematic friendships. However, greedy methods can fail in edge cases and are not guaranteed to produce the optimal solution, making them less reliable. The chosen strategy for this problem is the optimized approach using set operations because it strikes a balance between simplicity and efficiency. The core insight here is that we only need to focus on problematic friendships and the people involved, rather than repeatedly checking all friendships. By leveraging set operations, the approach minimizes unnecessary computations, ensuring scalability for larger datasets. One key observation that simplifies the problem is recognizing that only friendships lacking a shared language need to be addressed. Additionally, pre-computing the set of individuals involved in these friendships allows us to efficiently iterate over the languages and identify the optimal solution. While this approach is slightly more complex to implement than brute force, it is significantly faster for larger constraints. The brute force method, while easy to code, becomes impractical for inputs with high values of M or K due to its inefficiency. On the other hand, heuristic methods like greedy approaches may occasionally fail to find the correct solution. The optimized approach ensures correctness by explicitly addressing all problematic friendships, and its complexity of O, K plus M**n makes it suitable for inputs as large as 10 to the power of 4. This strategy is both comprehensive and efficient, leveraging problem-specific insights to minimize unnecessary computations while guaranteeing scalability. The problem we are tackling here is about enabling communication in a social network with the least effort. Imagine we have a group of people, and each person speaks a subset of available languages. Friendships exist between specific pairs, and for these friendships to be functional, the friends must share at least one common language. Our goal is to figure out the minimum number of people who need to learn a new language to ensure that all friendships can communicate seamlessly. To solve this, we need to analyze the languages spoken by each individual, identify where communication gaps exist, and determine the most efficient way to bridge these gaps by teaching a single language. This approach minimizes the overall teaching effort required to connect the network effectively. To approach this problem, the first step is to identify which friendships have communication gaps. For each pair of friends, we check if there is any overlap in the languages they speak. If there's no shared language, this pair is marked as having a gap. Using set intersections is key here, as it allows us to efficiently determine if two sets of languages have common elements. Next, we need to evaluate the usefulness of teaching each language. To do this, we create a frequency map that tracks how many people in these gap pairs would benefit from learning each language. This involves iterating through the gap pairs and adding both friends to a set of candidates for each language they don't already know. By collecting this data, we can quantify how impactful teaching each language would be. Now, we simulate the impact of teaching each language. For each language in our frequency map, we calculate how many unique people would need to learn it to resolve all the communication gaps. This is done by simply taking the size of the candidate set for that language. Once we have this data, the next step is to choose the most optimal language to teach. The optimal language is the one that requires the fewest learners to bridge all gaps. This step involves a single pass over the frequency map to find the language with the smallest candidate set. Finally, the result we output is the number of people who need to learn the chosen language. This represents the minimum teaching effort needed to ensure all friendships can communicate effectively. There are several key insights that make this algorithm efficient. First, using set operations like intersections allows us to avoid redundant computations and nested loops when checking for shared languages. Second, by pre-computing the frequency map, we eliminate the need to recalculate the benefit of teaching each language repeatedly. The approach is inherently greedy, as we prioritize the language with the highest utility, meaning the fewest learners required. This ensures an optimal solution. Additionally, we must account for edge cases, such as when all pairs already share a language, meaning no teaching is needed, or when no pairs share a common language, requiring significant teaching effort. Special scenarios, like individuals who speak no languages, also need to be handled carefully to avoid errors. To implement this solution effectively, we rely on specific data structures. Set intersections are used to check if two friends share a common language, offering both efficiency and simplicity. A hash map, or frequency map, is essential for tracking how many people would benefit from learning each language. This allows us to quickly determine the optimal teaching effort. Additionally, candidate sets are maintained for each language, storing the individuals who need to learn it. These data structures help minimize redundant computations and ensure accurate counts. Analyzing the complexity, the time taken to check all friendships for gaps is proportional to the number of friendships multiplied by the average number of languages per person. Building the frequency map and counting candidates also follows similar complexity. Overall, the approach is efficient, balancing time and space requirements. Let's walk through an example to clarify the algorithm. Suppose we have 4 people with the following language sets: person 1 speaks language 1, person 2 speaks language 2, person 3 speaks languages 1 and 2, and person 4 speaks language 3. The friendships are defined as pairs 1, 2, 2, 3, and 3, 4. First, we examine these pairs for gaps. The pair 1, 2 has no common language, so it's a gap. The pair 2, 3 shares languages 1 and 2, so it's not a gap. The pair 3, 4 has no common language, making it another gap. Next, we build the frequency map. For the gaps, we see that teaching language 1 would benefit persons 1 and 4, teaching language 2 would also benefit persons 1 and 4, and teaching language 3 would benefit person 3. When we simulate teaching, we find that teaching language 1 or 2 would require 2 learners, while teaching language 3 would only require 1 learner. Thus, the optimal solution is to teach language 3 to person 3. The final result in this example is that we need to teach only one person a new language to enable communication across all friendships. This demonstrates the efficiency of our algorithm in minimizing the teaching effort while ensuring that all pairs of friends can communicate. By strategically identifying gaps and selecting the most impactful language, we achieve the desired outcome with the least amount of intervention. In this Python implementation, we start by importing the default dict module to help us later in the code. The solution is encapsulated in a class named solution, and the key function is minimum teachings. This function takes 3 arguments: n, which represents the total number of languages, which is a list where each person's known languages are provided, and friendships, which is a list of pairs indicating friendships between people. Inside the function, we define a helper function called can_communicate. This function determines whether 2 people can communicate by checking if they share at least one common language. Next, we convert the languages list into a one-indexed set representation. This makes language lookups more efficient and intuitive, as language indices now align with their natural numbering. We also insert an empty set at index 0 to align the indices with one-based numbering. Now, we identify all the friendships where communication is not possible. For each friendship pair, we use the can_communicate function to check if the 2 friends can understand each other. If not, we add this pair to the non_communicating_pairs list. If this list ends up being empty, meaning all friendships are communicable, we can immediately return 0 since no one needs language teaching. Finally, we initialize a list called language_teach_count, where each index corresponds to the count of people who would need to learn that specific language. The next step is to calculate how many people need to learn each language to resolve the non-communicating friendships. For each non-communicating pair, we iterate over both individuals and check for each language from 1 to n. If a person doesn't already know the language, we increment the count for that language in language_teach_count. This represents the potential number of people who need to be taught that language in order to eliminate communication barriers. Finally, we find the language that minimizes the total number of people to teach. By taking the minimum value from the language_teach_count list starting at index 1, we ensure that we only consider valid languages, as index 0 was reserved for alignment purposes. This minimum value is then returned as the result, giving us the fewest number of people who need to be taught a new language to make all friendships communicable. Here, we begin by importing the necessary packages and defining the solution class. Inside the class, we have the minimum teachings method, which is the main function that solves the problem. To start, we define a helper function called canCommunicate that takes two sets of languages as input and checks if there's any overlap between them. If the two sets share at least one common language, the function returns true, indicating that the two individuals can communicate. Otherwise, it returns false. Next, we convert the input languages array into a list of sets called language sets. This makes it easier to perform operations like checking if a person knows a specific language. We also add a placeholder set at index 0 to ensure the list is one-indexed, since the problem assumes that languages are numbered starting from 1. Finally, we initialize a list called non-communicating pairs to store pairs of friends who cannot communicate with each other. These are the friendships we will need to resolve by teaching new languages. We then iterate over the friendships array to identify pairs of friends who cannot communicate. For each friendship, we retrieve the language sets of both friends and use the canCommunicate helper function to check if they share a common language. If they don't, we add the pair to the non-communicating pairs list. Once all friendships are processed, we check if the non-communicating pairs list is empty. If it is, it means all friendships are already communicable, and we can return 0 because no teaching is needed. However, if there are non-communicating pairs, we proceed to calculate the potential teaching effort. We initialize an array language teach count to track how many people would need to learn each language. For every person in a non-communicating pair, we loop through all languages and check if the person does not already know that language. If not, we increment the count for that language in the language teach count array. This helps us determine the total teaching effort required for each language. At this point, we need to determine the minimum number of people to teach a single language so that all non-communicating friendships can be resolved. We initialize a variable min teachings with the maximum possible value to keep track of the smallest teaching effort found. Then, we iterate through all the languages from 1 to n and update min teachings by comparing its current value with the teaching count for each language in language teach count. This ensures that we find the language that requires teaching the fewest number of people. Finally, we return min teachings as the result, which represents the minimum number of people we need to teach in order to make all friendships communicable. In this example, we are given 3 languages and 3 people, each knowing only one unique language. The friendships are defined as pairs, or person 1 is friends with person 2, and person 2 is friends with person 3. To start, we convert the list of languages into sets for easier manipulation. Since indexing in the problem begins at 1, we insert an empty set at the start to make the list 1-indexed. Now, for each friendship, we check if the 2 people in the pair share a common language. For the pair 1, 2, person 1 knows language 1, and person 2 knows language 2, which means they do not share a common language. We add this pair to the list of non-communicating pairs. Similarly, for the pair 2, 3, person 2 knows language 2, and person 3 knows language 3, so they also cannot communicate. The final list of non-communicating pairs is 1, 2, 2, 3. Next, we calculate how many people would need to learn each language to make communication possible. We initialize a count array with zeros, 1 for each language plus a dummy index at the start. For the pair 1, 2, if person 1 learns language 2, we increment the count for language 2. Alternatively, if person 2 learns language 1, we increment the count for language 1. For the pair 2, 3, if person 2 learns language 3, we increment the count for language 3. If person 3 learns language 2, we increment the count for language 2. After processing all pairs, the count array becomes 0, 1, 2, 1. Finally, we exclude the dummy index and find the minimum value in the array. The smallest value is 1, meaning we can achieve communication by teaching either language 1 or language 3 to one person. The output is 1. In this example, we have 2 languages and 3 people. Person 1 knows both languages, person 2 knows only language 1, and person 3 knows only language 2. The friendships are defined as person 1 being friends with person 2, and person 2 being friends with person 3. Converting the list of languages into sets, we create a one-indexed list by inserting an empty set at the start. Now, for each friendship, we check if the two people in the pair share a common language. For the pair 1, 2, person 1 knows languages 1 and 2, while person 2 knows language 1, so they share language 1 and can communicate. For the pair 2, 3, person 2 knows language 1, and person 3 knows language 2, which means they do not share a common language. We add this pair to the list of non-communicating pairs, which is now 2, 3. Now, we calculate how many people need to learn each language to resolve the non-communicating pair. We initialize a count array with zeros for each language. For the pair 2, 3, if person 2 learns language 2, we increment the count for language 2. Alternatively, if person 3 learns language 1, we increment the count for language 1. After processing this pair, the count array becomes 0, 1, 1. The minimum value in the array is 1, meaning we can achieve communication by teaching either language 1 or language 2 to one person. The output is 1. In this example, we again have 2 languages and 3 people. Person 1 knows both languages, person 2 knows only language 1, and person 3 knows both languages. The friendships are defined as person 1 being friends with person 2, and person 2 being friends with person 3. Converting the list of languages into sets, we make it one-indexed by inserting an empty set at the start. Now, for each friendship, we check if the two people in the pair share a common language. For the pair 1, 2, person 1 knows both languages, and person 2 knows language 1, so they share language 1 and can communicate. For the pair 2, 3, person 2 knows language 1, and person 3 knows both languages, so they also share language 1 and can communicate. Since all pairs can already communicate, the list of non-communicating pairs is empty. Finally, since there are no non-communicating pairs, no language teaching is required. The count array remains unchanged, and there is no need to calculate the minimum teaching requirement. The output is 0, indicating that everyone can already communicate without learning any additional languages. To analyze the time complexity, we begin by breaking down the solution into its key steps. The first step is pre-processing the languages list. Here, we convert the input into a list of sets for easier comparison and insert an empty set at index 0 for convenience. If there are m people and each knows up to k languages, this pre-processing step takes m*k, because we process each person and their known languages. Next, we identify non-communicating friendships. For each friendship pair, friend 1, friend 2, we check if the two individuals share any common languages. Since there are f friendships and each comparison involves up to k languages, this step requires f*k time. Finally, we determine the language teaching requirements. For every non-communicating pair, we consider each individual and iterate over all n languages to count the number of people who would need to learn a particular language. With up to f non-communicating friendships and n iterations per person in each pair, this step contributes f*n to the complexity. Once the teaching requirements are calculated, we identify the minimum language teach count. This involves finding the smallest value in the language_teach_count array, which has a size of n. Performing this operation takes n. When we combine these steps, the overall time complexity is dominated by f*k plus n, where f is the number of friendships, k is the maximum number of languages known per person, and n is the total number of languages. Now turning to the space complexity, the algorithm requires space for several components. First, storing the languages list as sets takes m*k, as we need to represent the language knowledge of all m people. Second, we store the non-communicating friendships in a list, which requires f space, as it contains at most f pairs. Lastly, the language_teach_count array, which tracks teaching requirements for each language, uses n space. These components together give an overall space complexity of m*k plus f plus n. When we step back to compare the optimized solution with a brute force approach, the difference in efficiency becomes clear. A naive brute force method would involve iterating over all possible subsets of people and simulating the communication process for each subset. This would mean an exponential time complexity of O2 to the power of m times f times k, as we'd have to consider all subsets of m people. In contrast, the optimized approach narrows the focus to only non-communicating friendships and calculates the teaching requirements efficiently. With a time complexity of O, f asterisk, k plus n, and a space complexity of O, m asterisk k plus f plus n, the solution avoids unnecessary computations and remains practical even for large inputs. To further refine our understanding, let's examine the best, average, and worst-case scenarios. In the best case, all friendships are communicable, meaning no one needs to be taught a new language. Here, the algorithm skips the counting step altogether, reducing the time complexity to O, m asterisk k plus f asterisk k. On the other hand, the average and worst cases occur when some or all friendships are non-communicating, requiring the algorithm to perform the full counting step. In these scenarios, the time complexity becomes O, f asterisk, k plus n. This analysis underscores how the dominant term in the complexity depends on the number of friendships f, the maximum languages per person k, and the total number of languages n. By focusing exclusively on non-communicating friendships, the algorithm avoids redundant computations and maintains scalability for large datasets. When tackling this problem, there are several common pitfalls to watch out for. First, failing to consider all friend pairs can be a major oversight. It's not enough to just focus on direct communication, every friend pair in the input needs to be evaluated to ensure they share a common language. If even one pair is missed, the solution could be incorrect because the ultimate goal is to guarantee that all pairs can communicate. Another mistake is inaccurately updating the language count. When deciding which language to teach, you need to precisely track how many people already know each language. Incorrect counts can lead to the wrong language being chosen, which increases the number of people that need to be taught unnecessarily. Additionally, assuming symmetry in friendships can lead to trouble. While many problems involve bidirectional relationships, this one may include directed friendships, so make sure your graph traversal respects the given directionality if it's specified. Lastly, be cautious of using inefficient solutions when dealing with large inputs. High time complexity approaches, like O, n cubed, may work for smaller cases but will fail with larger datasets, potentially resulting in time limit exceeded errors. Always aim for algorithms that can handle the upper bounds of the input size efficiently. Now, let's consider edge cases and some strategic insights for this problem. Overlooking edge cases is another frequent issue. For example, you might encounter scenarios where everyone already shares a common language, or conversely, where no one knows any language in common. Skipping these edge cases can lead to incorrect results, so it's important to handle them explicitly. A key insight to simplify the problem is to focus on maximizing the number of friend pairs who already share a language. By doing this, you minimize the teaching required. Friendships can be visualized as a graph, where each person is a node and edges represent friend pairs. This graph-based perspective makes it easier to analyze relationships. When selecting the language to teach, you can use a frequency-based approach to identify the language that connects the most people with minimal effort. To optimize the solution further, track which friend pairs can already communicate, avoiding redundant checks. For additional practice, you can explore related problems on LeetCode. For instance, problem 997, Find the Town Judge, involves analyzing relationships in a graph, while problem 886, Possible Bipartition, focuses on partitioning graphs. Other relevant problems include 1057, Campus Bikes, which deals with pairing optimization, and 841, Keys in Rooms, which involves graph traversal to ensure access. To approach this problem, there are a few alternative strategies worth considering. A brute force approach would involve evaluating all friend pairs for each language and counting the minimum number of people to teach. While this method is straightforward to implement, it becomes highly inefficient for larger inputs due to its high computational cost. A more efficient option is to use hash maps to count how many people each language enables communication for. This approach reduces the complexity to O, n asterisk m, making it suitable for larger datasets, but it does require careful implementation to avoid errors. Another advanced method is to use a union-find data structure. Here, you group people based on the languages they know, and then calculate the minimum teaching required. While union find can be powerful, it adds complexity in terms of implementation and might not always be necessary depending on the problem size. Each approach comes with its own trade-offs, so it's important to choose the one that best balances efficiency and simplicity for the given input constraints. Great job! In this session, we tackled the minimum number of people to teach problem, breaking it down step by step. Hopefully, you've gained insight into graph-based problem solving, optimization strategies, and the importance of clear problem modeling. Thanks again for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!